Welcome to The Explainer. Today, we're talking about an invisible threat, one that's all around us. It's the silent weakening of those massive walls you see holding back tons of earth along our highways. But what if we could see inside them? Well, some new technology is giving us a way to do just that, and it could stop disasters before they even begin. So, let's just start with a really basic question. When you look at a huge retaining wall like this one, supporting all that earth right next to a busy road, how can you be absolutely 100% sure that it's solid all the way through? The honest answer? You can't. And right there, that uncertainty, that's the heart of the problem we're diving into. It all starts with the dangers that our eyes just can't see. What you see on the left is what traditional inspections look for, stuff on the surface. But look at the right. That's where the real trouble is brewing. Behind that wall, the soil can start to loosen, water pressure can build up, and this can create something called a slip plane. It's basically a weak layer where a whole chunk of earth could just decide to shear off and collapse. These are the real causes of failure, and they are completely, totally hidden from view. And look, this isn't just speculation. The inventors of this new method say it perfectly in their patent. The main problem happens in the soil behind the wall, where you can't observe it. We're basically trying to judge the health of this massive structure just by looking at its skin.
So, the big question is, how do we see the invisible? Well, this new patent proposes a brilliant solution. It's almost like giving the wall a CT scan, letting us finally peer deep inside. The technology is called a multi-point extensiometer. Now, don't worry about the fancy name. What it does is pretty revolutionary. It's a set of sensors that are installed deep inside the wall to measure tiny, tiny movements. And this gives us something we've never really had before: actual, hard, quantitative data on what's going on inside. And this right here is a total game changer. It takes us away from just making educated guesses based on surface cracks and moves us into a world of clear, data-driven understanding of the wall's actual stability. We can track changes over time and make decisions based on real numbers, not just what it looks like on the outside. All right, so let's get into the nitty-gritty. How does the system actually work? We're going to break down how it's put together and how it pulls that critical data from deep inside the earth. What's really cool about this is how elegantly simple the concept is. It's basically a three-part chain. First, you have anchor plates. These are put at different depths inside the soil to act as fixed measuring points. Then, you've got these wires that connect those deep anchors all the way out to the surface. And finally, there's a little measurement unit on the face of the wall that precisely reads any tiny movements that get transmitted up through those wires. So simple, but so incredibly effective. Now, if you're building a brand new wall, it's super easy to just build the system in from the get-go. But what makes this technology so powerful is that you can also retrofit it into the thousands and thousands of existing walls that are already out there. And they don't just go drilling in blind. To install this on an older wall, engineers follow a really careful process. They'll review the original blueprints and then use tools like ground-penetrating radar to actually map out where all the hidden steel or reinforcements are. This lets them drill safely without damaging the very structure that's holding the wall together. Okay, so this is where the real innovation kicks in. It's not just about collecting a bunch of numbers. It's about turning that raw data into clear, actionable intelligence that engineers can actually use to make critical decisions. The system calculates 5 key things. For instance, it doesn't just tell us if the soil moved. It tells us the displacement velocity. In other words, how fast is it moving right now? That can be a huge warning sign. It can even estimate the exact location of that hidden slip line we were talking about earlier. And this right here, this graph, is the aha moment for the engineers. It's plotting how much the soil has moved versus how deep it is. And that sharp bend in the line, that kink that we've highlighted, that's the smoking gun. It can precisely pinpoint a hidden slip line, the exact spot where a future collapse might start. All that data then feeds into this really simple 3-tiered warning system. You can see the original Japanese terms from the patent here, which translate basically to caution, alert, and consider measures. It's a super straightforward framework that tells the people in charge exactly how to respond based on the real data. So what you get is this complete feedback loop. You start with a visual check, then you use the system to get hard data, you analyze it, make a decision, and then, and this is so important, you use the exact same system to verify that your repairs actually worked and made the structure stable from the inside out. So let's zoom out. What does this all mean for the bigger picture?
Well, it's about a fundamental shift in how we manage the critical infrastructure that we all rely on every single day. Essentially, it lets us move from being reactive, waiting for a wall to start bulging or cracking before we do something, to being genuinely proactive. We can monitor its internal health and fix weaknesses long before they ever become dangerous failures. At the end of the day, this isn't just about some clever engineering. This is about preventing catastrophic failures. It's about saving a ton of public money on emergency repairs, and it's about making our infrastructure last longer. But really, the most important thing is that it's about keeping people safe. And that leaves us with one final thought. As our roads and our bridges and walls get older and older, what other invisible risks are lurking just beneath the surface? And what new ways are we going to have to invent to see them?